Deepti. I'm an assistant professor at Boston University. Very excited to be here. Um, oops, let me see. Okay. So I work on um, generative and reasoning multimodal models, and that's a very broad spectrum. And that involves studying all of these different aspects and components of these models. So these have been some of the questions that we've been thinking about as to like what aspect of MLLMs or multimodal models should we care about, should we study and deeply understand. This talk will focus on two aspects. One is um, improving or understanding more about the reasoning capabilities of MLLMs. And I'll talk about how we approach that in this particular paper, which is titled Some Modalities Are More Equal Than Others. And then also talk about efficiency, how to make generative video models, particularly more efficient. And in that context, I'll talk about DDIT or dynamic DIT, which was a CVPR highlight given to maybe like the top 2.5% of the submissions. All right, so jumping right into making generative video models more efficient. Um, uh, Inference, even inferring or generating a video, which is just 5 second long, 720p, takes 30 minutes on RTX 4090. So this itself is time consuming, and the reasons folks who work in this space are quite familiar with it. Diffusion is an iterative denoising process. So during inference, we start from a noisy image or a noisy latent, and then iteratively try to remove noise to the point that we get like a less noisy image, lesser noisy image, and then like the pure signal that we are after. And the same algorithm applies in the context of videos. And then each step, every time we're doing this denoising, we process every spatial token in within the entire image, and that also is expensive. So this made us wonder if every image should it be encoded at the same granularity. Well, let's think about this, right? Because images have very different semantic complexity. Take a look at this. I meant to turn on the laser point. Yeah. Take a look at this image where though the bag is nicely detailed, the background is quite plain. And compare that with this painting, for example, where almost every corner of this image is very fine grained, is highly detailed. So even in one particular image, this is of this kitten, you would see that there are certain regions which have high texture, especially the furry regions of the cat, and there is this bokeh effect which may not require the same amount of compute when we're talking about spatial tokens. So this could be one way we could divide this image as opposed to allocating equal budget to every image. So the takeaway from this thought experiment was every image is not equal. We don't have to encode them with the same amount of compute, and different regions can be encoded with different levels of spatial granularity. The second question we had was, well, at this point, this is our pipeline, right? We take image, divide it into equal size tokens, and we denoise it. Does every denoising step should it process the image at the same level of granularity? So what do we mean by that? So there are works, some that we have studied, and some of like our colleagues, which have established that the way image or video evolves during the generation process is non-uniform. in that the earlier time steps try to sort of paint out the course scene layout, and it's only in the later layers that the finer grained details are painted in or are generated. So to be more precise, earlier time steps focus on course layout and scene composition, while later time steps focus more on sharpening the texture. So, given this, let's revisit our question number two, which is, should every denoising step process the image at the same level of granularity? And the answer to that also seems not necessarily. So, two questions, and the answer seems not necessarily. Um, so the that brings us to our core idea, which is, well, if this is the case, then should we and can we dynamically vary the path size based on the denoising time step and also based on like the scene complexity? So this is the core idea behind our work. And as talked before, this is our baseline where every time step is like processes the image at same level of granularity. And what we're shooting for is this is our this is our dream. This is what we want to achieve, where maybe there will be certain time steps, presumably the earlier time steps, that process the image at coarser granularity. There will be the time steps which are more closer um, to zero, where we do process it at finer granularity. Um, and as you can see here, if in the baseline, the cost for every time step is fixed, you'd notice that the cost in the proposed or our goal dream framework uh, would be would be cheaper in certain steps and would be the same as the baseline in certain other steps. This is our goal. Figure out how to dynamically vary the path size based on content and time step. Um, but why dynamic? Let's go back here and do exactly this, right? Let's maybe allocate, let's just say that, okay, the first one third is very coarse, the second one third is just moderately coarse. So we tried doing that, hoping to see maybe that is enough. We don't need anything algorithmic. So this was a prompt, a red colored car, and this is the baseline using Flux Def. And this is what we got when we did this manual scheduling. This is not a cherry picked example. This is something that we've seen consistently. So it does align to the prompt, but the level of detail that we have here is kind of getting lost. And our goal is to be as close to the baseline in terms of the generation quality, but um, be as computationally efficient as we can. Um, so, how do we do this? Our hypothesis is can we use the latent rate of change as a proxy to understand if there's a lot going on or if it's a slowly evolving, it's a slow scene layout that's being painted out. So let me break this down further. Let's say um, this is the latent. So I show the image, but we operate in the latent space. So this is the latent at time t. This is the latent, let's say, at the previous time step t minus one and t plus one, which is a future latent. Um, Displacement is would be like just the first order difference between the t plus one and t latent. Velocity would again be rate of change of displacement, and acceleration is rate of change of velocity. So we are still operating in finite order differences in the latent space. Um, so we measure, so at a given patch granularity for a latent, we measure acceleration. at different patch sizes. So let's say we do compute how every patch evolves, the acceleration at every patch for this patch size 2. And then we compute standard deviation of this acceleration. And our hypothesis is if the standard deviation is low, then maybe not a lot of change has occurred because the acceleration has not varied that much. So we sample a slightly higher path size. So we compute the acceleration at path size 4, and then again compute the standard deviation of it. And then let's just say that the standard deviation is still low, which means that something in that patch is evolving very, very slowly. And hence we can extract, uh, we don't have to allocate as much compute as needed. So we try a higher coarse grained patch size. So we repeat this until the standard deviation hits like a particular threshold that we've determined empirically. So again, like our hypothesis is if the latent is changing rapidly, then that means something finer grained texture is being generated. So we will allocate the smallest patch size so that we don't lose the generation capability. And if the latent is evolving slowly, then well, let's extract the compute and make this more efficient. So I this example might further ground this. Along the x-axis are the different inference steps, and along the y-axis are the different patch sizes that we dynamically vary during inference. So let's follow the blue line, and this is the image. As you can see that though the background has a bokeh effect, there is rich texture in this image. So this is which would require a good amount of compute. So you would notice that for the earlier time steps, the model we were able to get away with patch size of 4, but in the mid and towards the end, we ended up constantly using only either patch size 2 or 1, presumably because of the finer grained zebra patterns. Um, I'll switch to the third image, which is more stark, where it's just a very plain background and just an apple. So a lot of smooth regions. And that's evident in the fact that not only the earlier time steps, but also the mid and some of the end, we were able to get away with like a higher patch size, and hence um, leading to like a speed up in generating this. So our observations here is if the region is high textured, there is the latent evolves more quickly, and hence we do stick to allocating smaller patches to it. And if there are smoother regions, then our method quickly switches to higher or larger patch sizes, and that gives us gains in the compute. All right, so here are some results. So we compare against caching based, token compression based, and also in the paper distillation based methods. But DDIT is a proposed algorithm. The number in the brackets indicates the amount of speed up we attained compared to the baseline. So 2.2x indicates generating this was 2.2x times faster than generating the baseline image. Notice that Tcache, a popular like caching based like inference speed up algorithm, uh, we get the same gains in terms of speed up, but notice that there is a loss in aligning to the prompt that was asked. So here it was a dog, but the object changed to something else, teddy bear. Same with Taylor's here, another speed up algorithm. where again, like we do match the speed up. We get like 3.5x uh, uh, boost, but then you notice that the finer details in the legs, for instance, are are lost. The shape of the object has also shifted. Same observations here. Maybe this isn't translating well via Zoom, but these are blurrier images compared to what we see here by the DDIT generations. Um, So another example, this which was also an interesting finding, where this is the baseline. Again, all of them we get roughly 2.2x speed up, but there was shift in the color distribution overall in the image. These two, for some reason, the object orientation shifted from like a side viewing to like a front facing elephant. But yeah, like our particular model was able to like retain all of these like important finer grain details, the spatial layout, while also achieving the same computational speed up. So this is when we applied our results to video model. On the left is 1 2.1, our baseline, and on the right is DDIT with like 3.2x speed up. Um, we did human studies, we did SSIM, CLIP, and all of the quantitative evaluations. And the users were um, not able to figure out if there was no preference of like one generation over the other, which means that perceptually, uh, both like the DDIT generations and the baseline generations looked very similar. Failure cases very quickly. If the baseline generation itself struggles to align with the prompt, if it has like struggles with spatial relations, briefly, then it's hard to undo that failure just because of the computational speed ups that we do. Anyway, um, DDIT, the QR code has like the code base, more image and video results, and a lot more like qualitative and quantitative examples. Not all time steps are equal. We dynamically select the path size at every time step during inference based on how the latent has evolved, and then we achieve significant gains with like minimal loss of visual quality. So this work was driven by my student Dahe. Um, I do have 2 minutes, so I'll quickly, very briefly introduce the other work, which touches on reasoning. Um, so again, like multimodal models, they talk about how all three modalities like interact and uh, are fused towards like particular reasoning tasks. And the modalities I've been focusing on is vision, language, and audio. So this is our like baseline case. The question that we are interested in is what happens if one modality is in conflict with one another? This can happen unintentionally, like we're watching, um, let's say, a sports video, but a completely different audio is overlaid on it. Um, or it could be an intentional attack where it is maybe a safe video, just of maybe a child playing, but then someone tried to insert like hate speech into it just as a way to attack the model or um, with bad intent. So these were our like motivating cases. And whoops, we tried to design dataset which will have aligned samples and misaligned samples. So aligned would be the case where the video is that of a dog barking, and the labels would be describe the object based on the audio, two questions, and the answer would be dog. and describe the object based on the audio, that would also be done. And then we generated misaligned samples where the audio is intentionally misaligned with that of the video. So here is the video shows that of a cash register, but the audio is that we removed the original audio and then inserted a misaligned audio of that of a printer. So four scenarios. This is our baseline where all three modalities are aligned. Video shows a bell, audio has bell, and the text caption also has a bell. Video and audio are misaligned, but text says the same. So video has bell, but the audio is that of a dog barking. Um, Video and audio are aligned, but then we've just inserted misleading text. And then again, like video and audio are aligned, but we just inserted completely irrelevant text. So these are the four scenarios that we studied, and we constructed a data set, a benchmark called MMA bench, multimodal misalignment study benchmark. And then we probed different models, open source and closed source. And then we found that many models, they struggle a lot when just even one modality is misaligned. So here we swapped the audio with an irrelevant one, but then the question still remained, what is the object that you see in this video? And then we saw that there is a drop of 20% in the performance. So even though the vision modality has not been tampered, the visual reasoning definitely gets impacted because of this cross-model misalignment. And similar observations were found in audio prompt when we said, what object do you hear? Then even there, we found a 20% drop in the performance. So it indicates that, well, there is integration of modalities, but then the conflicting modalities do lead to uh, uh, like a poor performance. We've seen similar things in the case of like another model, which is Gemini, and then also when vision and text are misaligned. So here is an example where audio, video have been intact. It's just the text has been messed up. The caption has a distracting word added to it. And that alone was enough to lead to like a 20% drop in the performance and a much larger performance in the audio. This was surprising to us because the video and audio were intact. It's just the text where we inserted just one word that was irrelevant. So that indicates that there is a clear modality domination in these models. So text dominates everything, followed by video and then audio. So the benchmark is called MMA bench. The students who drove this are Chaitanya and Tianle. The project page is very well designed. It has a bunch of several qualitative and quantitative examples. The students have studied a lot of different like black box and white box analysis. And the key takeaways are MLLM struggle when even one modality is misaligned. So it is important to stress test these models on these like corner cases before deploying them on like safety critical situations. So yeah, here are the two papers, and then the QR code points you to the papers, and happy to take any questions.